Hello students, welcome you all to the series of CFD tutorial. In this series we are going to learn about some CFD problems. In that we will use Ansys Workbench software, and from this we will use Ansys Fluent solver. So here for our first tutorial we are going to learn about Blasius equation. So here you can see we are using this physical model. So here we are focusing on boundary of the flow over a flat plate. So this is a flat plate. So it is having this length is 0.5 meter, and here is zero point 0.5 plus 0.25, that is 0.75 So here what we are considering under boundary condition is that fluid is air, and properties are given here. So here air is flowing through over this flat plate with initial velocity 1 meter per second. Reynolds number is given here, that is 3.5 into 10 raised to 4 at the end of plate. So entire boundary layer is laminar. So how we can define type of flow? It is depending upon Reynolds number. So depending on Reynolds number, this flow is a laminar flow. Okay, so we are using laminar model for this problem description. So here boundary conditions are given, inlet velocity is given, then top velocity, then symmetry boundary condition is given already, then outlet is defined here. Okay, then here pressure is given 0 pascal relative to atmospheric pressure, and flat plate no slip wall boundary condition we have to use. Okay, and steady solution is obtained using pressure based coupled pseudo transient solver in Ansys Fluent. Okay, so for that students, what we have to do, we have to go into Ansys Workbench. Now here there are two cases where you can do CFD analysis. So first case is that in this you are creating geometry by your own, and after creating geometry you can perform analysis on that geometry. So this is a case one, and second case is that you have already mesh file for your analysis. You can directly import your mesh file irrespective of geometry, and then you can perform analysis on that. So if you see here you can see one analysis system called as a fluid flow fluent. So if I drag it to project schematic window, you can see here geometry option is there. So for our case one, you can use this analysis system, that is fluid flow fluid. Okay, but for second one, what you have to do, you have to go into component system here, and here you have to select fluent from this. Okay, so these are two cases basically. Now if you see our problem, you can see below. Here we are going to import a mesh file directly. Okay, so for that purpose you have to use a second case, means you have to directly use fluent system from component systems, right? Now we'll go here. I'll delete this because we are not creating geometry, we are directly importing mesh file. So for that, in this setup we have to go. So you just have to right click on to setup, click on to edit. Okay, here Fluent launcher is opening. So before opening Fluent launcher, you have to select certain parameters, like you have to define which type of problem you are solving. So this is a 2D problem, so I'll select 2D over here. Then under options, double precision you can turn on for more solution accuracy. Okay, so I'll turn it on. Then display setting, display mesh after reading. Okay, then load ACT is not needed here. ACTs, Ansys customization tools are there. Then processing options, serial and parallel. So currently we are running this on single system, so serial will use, and click on to OK. So it will open Fluent launcher, and it will take some time for opening. So here we'll see steps which are needed for that till then. So if you see here, you just have to allow all the access. Okay, Now here first of all you have to import mesh and check its quality. Okay, then we can display the mesh. Okay, so these are certain steps. So first, minimum orthogonal quality we need to check, and it is needed to be greater than zero point 0.1. So we can determine that mesh has a good quality. Okay, so here Fluent launcher is open now. Okay, so you can close this from here, just maximize it. Okay, now this is its interface. Now from file you can import. In file you have to go here, import mesh. Okay, now mesh file you need to select. Okay, so this file we need to select, that is flat plate msh, and click on to OK. Okay, now this file will load here. Okay, so this is our mesh file basically. Okay, you can zoom in here and see the mesh density. Near to all, it is a very fine meshing we are having. Okay, done. Now we have to check its quality. So for quality checking, what you have to do, you have to go here, under general, click on to check. Okay, here in under check you can check its maximum and minimum face area. So just ensure that your minimum face area value and minimum volume value, that should not be under negative. Okay, so it is having positive value, so you are have good to go for next step. So you can select on to report quality. Then here if you can see, minimum orthogonal quality is 1.00 exponential 00, so 1 it is basically. So it is 0.1 you can say. So it is good quality mesh already we are having. Now next step is of displaying mesh. So you can display mesh. So you just have to go on to display here, uh, select these options and display. So mesh is already displayed, so no need to display it again. In case if you don't see mesh here, then you can use mesh display option. Now after that, what you can do here, you can observe that grid is comparatively dense near the wall to capture the boundary layer characteristics. So that already we have discussed. Okay, now next what we can do here is we can keep these values default. So here in problem description, pressure based solver system is used. Now, as mentioned in our problem, we have to use pressure-based solver, and all the settings are as it is. Steady state we are going to use planar 2D space and absolute velocity formulation. Okay, so this is for general. Now, next what we have to do, we have to select our model. So as flow is laminar, we are going to use laminar model here. Okay, so we'll go here. Now under this setup you have to go into models. Okay, so models, I'll just double click over here, and under viscous here, laminar, it is already selected. So if you see here, you have to select laminar. Okay, then materials. Okay, so model is laminar. Now after that we have to go into material. So here you can click on to materials. Okay, and here which material we have to use is air, so you can just go for air. Okay, and here this values means density, viscosity, that values we are keeping as a default. Okay, just close this. So material is already present with us. Now we have to use boundary conditions. So here under cell zone conditions, fluid. Okay, here fluid is already used. Okay, fine, no issues. Now we are going to uh, apply boundary conditions. So under boundary conditions, if you see, change the velocity specification method to components. Okay, so for which here we have to go on inlet. Okay, so I'll just sort it out. Zone type and inlet. For inlet we are going to see. So you can either double click onto inlet or just select inlet and go on edit. Okay, so here velocity specification method we have to set as a components. Okay, then next step what we have to do is set x velocity to 1 meter per second. So here x velocity 1 meter per second. Okay, done. Now next what you have to do, change the type to pressure outlet. So on outlet you have to go. Okay, I'll click OK over here, go on outlet, then type you have to change for boundary condition, that is pressure outlet. So go here and see where you can find here pressure outlet. Okay, now after going into pressure outlet, you just have to click OK over here, and in wall you can see top F. For top F, select velocity inlet here. Okay, here you can see top F velocity, you have to make velocity inlet. Okay, and here just click on to okay, so this top F will be added here. Okay, here x velocity we need to change, so here same settings we have to do, components and x velocity 1, and click on to OK. Okay, now next is set reference values. So reference values you can set from top. So for that you can go in physics and here reference values. So set the reference value for correct dimensionless value calculation in post process. Okay, so just see values are already defined here, so you just have to check and change values if necessary, but here default values are okay, so no need to change. Now next is what, solution methods. So here on left hand side under solution on methods we have to go solution methods. So here pseudo transient, you have to ensure that it is turned on. Okay, the rest of the things are similar. Okay, now after that next is residual monitors. Okay, now residual monitors you can use from monitors, residual monitors. Okay, for residual monitors ensure all values are currently given here. So you can just change values to 1 exponential minus 6 over here, 1 exponential minus 6 for all parameters, 1 exponential minus 6 for x velocity and 1 exponential minus 6. Okay, then so you can just click OK over here, rest of the settings are same. Then under the report definitions you have to go, so I'll just click OK here, then report definitions. Okay, so for that where you have to go under solution here. So for solution report definitions, here you can go into new and uh, here new flux report and mass flow rate you need to select. So these are results we are going to plot. Mass flow rate. So for mass flow rate, here mass flow rate selection is there. Then okay, here you need to sort this, otherwise inlet and outlet conditions you need to select. So just a minute. Here three velocities you need to select: top F, top R, and inlet. Then for outlet, this outlet condition we need. Okay, select them, select inlet and outlet to check for mass balance within the computed domain. So these results, mass flow rate, will be plotted for inlet and outlet boundary conditions. Simple. So click on to OK. Okay, then yes, you can go in edit again. Mass flow rate for inlet, velocities, outlet, and symmetry. This for symmetry also. Okay, and you can rename it also mass balance. Okay, so this is report definition 1. Okay, here mass balance I will put mass balance. So in mass balance, what we have done, we have added symmetry as an additional parameter. Okay, and here report plot and print to console, that we need to turn on. Okay, then so under here reports it will be seen. So here for mass flow rate also we can edit it. Okay, like this. Okay, done. Now next step what we have to do is initialize solution. So in the solution you have to click on to initialize. So solution initialization will be done. So hybrid initialization we have done. Now number of iterations we will set to 500, 500. Okay, now you have to calculate the solution. Okay, and you have to wait till it gets solved. So reference values already we have seen from here. Reference values, solution control parameters are there already. Okay, now initialization is done. You can directly go on to run calculation. Okay, here run calculation is there. Okay, and you have to plot these results. Okay, so we'll see how to plot this all results. Okay, but first of all we'll move on to that solution step. Okay, so just click on calculate here and just see. So here you can see this, that residual values will be decreased at decreased by some uh, value, and you will get the notification as a calculation complete at 71th iteration. Okay, so this is a scaled residuals monitor. Okay, now calculation is complete. Okay, so if you can see we have obtained this graph, then this is also with us. Now velocity we can plot. Okay, now for velocity, okay, from reports we can do or vectors. Okay, so here results, vectors you need to select new one. Okay, so for vectors, which vector you have to create is for velocity, then velocity magnitude. Okay, then here scale you need to change to 0.03. 0.03. Okay, rest of the things are same, just save and display. Okay, just a region we have to select for which we want to see these results. Okay, velocity magnitude 0.03. Then suppose if we select all, okay, here color map options, log scale apply. Okay, color scale is already set. Okay, fine. So what we will do, we will plot at inlet, symmetry, and outlet. Suppose close. Okay, fine. This arrows and all scale I think is too low. So here scale 0.03. Okay, fine. Here all we will select suppose and display. Yes, this is boundary layers. Here if you see, just a minute, you just have to zoom over here and you can see this boundary layer formation. Okay, here you can see near to boundary it is having zero velocity and away from boundary velocity is increasing. So this is called as a boundary layer. So you just have to zoom in to see the exact effect like this. Okay, so this is boundary layer formation. Close this. Now next thing is what we have to plot contours. So you have to go under controls, contours, new, and here under contours select this contour lines will turn off, global range, auto range, velocity and x velocity. Now velocity magnitude we have seen, now velocity in x direction we'll see. Okay, and save and display. Okay, you will see this. Okay, here you can see easily boundary layer formation. Okay, so here in between there is no area of consideration for us. So here if you see, here there is a boundary layer formation. Okay, from this region to this region and at bottom also. Okay, so this is velocity in x direction. Now next one what we have to plot is we have to create lines. So these are just result parameters. You can plot multiple results from this. So you can create lines. So under surfaces here create a line rake. Okay, so just go on to create line rake and here create lines for x 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so if you see here x 0.1 to 0.5. Okay, so if you see here 0.1, 0.1, 0.1. Okay, then 0.5, 0.5 and y is 0.1 only. Okay, means here this lines we have to create x is equal to 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0.5. So 5 lines we have to create. So just go here line x is equal to 0.1. okay, so here 0.1, 0.1, and if you see for first is y also we have to keep as a 0.1, create. Then next line is what, x is equal to 0.2. okay, now 0.2 and x1 0.2 will create. Right here you can see at last 0.5, 0.5 they have selected. So create second line. Now third line x is equal to 0.3, 0.3, 0.3, create. Now for fourth one, x is equal to 0.4, 0.4, and 0.4, create. And last one, x is equal to 0.5, here x0, 0.5, and here this x1 is also 0.5 meter. Create and close. Okay, now after that what we have to do is we have to plot this xy graph. So in xy plot you have to go under plot, xy plot, new xy plot. We will plot for velocity, x velocity. Here velocity, x velocity, direction vector, node values 0, 1, plot direction 0, tab 1. okay, next thing is for line surface. If you go, you have to select all the lines. okay, rest of the things will be as it is. Save and plot. So you will see this plot. So this is basically with position you can see velocity is increasing up to certain value, and then after that velocity is constant. okay, close. So this is your xy plot. Now we'll create xy plot for walls. okay, wall fluxes. So under xy plot, new, okay, xy plot 2. Here what you have to do, 1 0 wall fluxes, and here static skin friction coefficient, and for walls you need to select. okay, done. Save and plot. okay, now we have plotted it for both. So you can eliminate this and again, sorry, wall plate. okay, like this you will get this. So here you can notice with respect to position, friction coefficient is decreasing, and at certain value it meets to 0 value. okay, okay, so these are results. okay, so this is our complete tutorial, friends, regarding analysis of flow over a flat plate. okay, so here what we have analyzed is a simple air flowing through a flat plate. okay, so hope you all have enjoyed this tutorial. Now we will meet in second tutorial. Till then you can try this and perform same on your system. okay, thank you.